Well, welcome back, everyone. We have 4 more weeks of quality time together. Plus, I guess the final we count that as quality time. Which is exciting for me. I don't know how you all feel. Hope you had a great spring break. Hopefully you got caught up or felt refreshed or whatever you needed to do that happened. So yeah, we got our test this Thursday. Hopefully it's not a surprise to anyone. So we have our test this Thursday, and then the 2 following weeks we'll start doing stuff with light and optics. And then kind of last week after that will just be kind of review / if we have any optics, but we'll probably finish in the next 2 weeks. So today I'm just going to do kind of a quick summary, 20-30 minutes of here are the things you need to be able to do. Big kind of sweeping gestures. Obviously, won't get all the fine details in that 20-30 minutes, but here are the key things you need to know how to do. I will then talk about the right-hand rules, because that's probably the trickiest part of the test. Not because I necessarily consider it tricky, but because it is so visual. Me teaching this to you all, if you're online, I tried, but the reality is it is such a visual thing of showing the hand. So I'm going to give a cheat sheet of hey, here's what I recommend putting down in your note card if you feel like you forget it. What finger points when, basically. And the best, shortest kind of summary I can think of doing. So I'll do that, and then, kind of look at some major problems, give you some examples of things you should be able to do, and if you have any questions, that you want me to do, I can do that as well. But let me do a quick overview of here's what you need to know. So there's 4 kind of things we talked about. What do you need to know? So the first thing we talked about was circuits. Circuits, series and parallel. Series and parallel for resistors and capacitors. Capacitors, you just need to know how to combine them if they're in series. So you need to know what series is. You need to know what parallel is. You need to know how to combine them if they're in series. Resistors, how do you combine those in series versus capacitors? How do you combine those in series? Those equations are given, but it's not labeled which one is the one for series and which is the one for parallel. So resistors in series, you just add. Capacitors in parallel, you just add. Resistors in parallel, you do 1 overs. Capacitors in series, you do 1 over. Right, so just, that's kind of, you know that. And then if you have a combination, remember there's that process. So if you have a bunch of resistors in series and parallel, you need to combine to 1 and then work your way back. Yeah.
Okay, we do not need to know RC circuits.
No, you do not need to know RC circuits. Promise. No RC circuits. Pinky promise, 100%. Do not need to know RC circuits. They were on a discussion. You do not need to know RC circuits, 100%. So if you have resistors in series and parallel, you have to combine to a single resistor and then work backwards. So this is one of those skills. This is one of the things you need to be able to do. You need to know how to, so let's just kind of make up a picture real quick. This guy, let's do this, that's not great. All right, so I have a thing with 4 resistors. Let's just call it 1, 2, 3, 4. Technically put an R next to it, but for the sake of time. And I say, find the current, kind of here, at this spot. Find the current there. No matter what I ask you, you should immediately recognize the way you solve these problems is you have to combine them into 1 resistor. So you figure out which ones you can combine. Oh, these are in series. Yay, I can combine those. So I combine those together. We'll call that 3, 4, which looks like 34, but 2 and 1. And then we say, oh, what do I combine now? Oh, these are in parallel. So I can combine those. Boom, boom. That's 1, that's 2, 3, 4. And then you say, oh, those are in series. So I can combine those. And this is 1, 2, 3, 4, resistor 1, 2, 3, 4. Why do we do this? Because if you do this, we know this resistance, we know this voltage, it gets the same voltage, you can find current, and then you can work backwards. So the current here will be the same as the current here and here, because they're in series. Then you can find the voltage, and there's a bunch of problems like you need to be able to take a circuit with a bunch of resistors, combine it to one, and remember the rules. In series, current is constant, in parallel, voltage is constant. In series, current is constant, in parallel, voltage is constant. So that's kind of the big one from circuits. Can you do this? This is a very important skill because it lets you find the current, voltage, and resistance of everything in the circuit. So, make sure you can do that. That's for circuits. And then we get into magnetic fields. So circuits, make sure you can combine things in series, make sure you can do things in parallel. There's also the junction rule. That one's really straightforward. I'll just kind of chuck one of those over here as well. Junction rule. Current in equals current out. What goes in must go out. If I have 20 students come into my exam, 20 students better leave my room at the end. No matter what doors they come in, if I have 10 students come in the top door and 10 students come out the bottom door, however it works out, 20 students need to leave somehow, some way. So, if I have a bunch of currents going here, let's say this one's 3, let's say this one's 4, let's say this one is 5, then that one needs to be 2. What goes in must come out. So, all right, great. Circuits, that's the gist of it. Major points, doesn't necessarily cover quite everything, but enough of it. And I'll post this after class as well. In fact, let me save this as I go because I'm doing so much writing. It'd be very sad if it all blew up on me. Boom. Boom. There's, oh, you can't even see them. All right. So, great. Circuits. Need to know that stuff. Magnetic fields. What do you need to be able to do when it comes to magnetic fields? You need to be able to find the direction and magnitude of the force on moving charges. That was a whole week we kind of spent on. Force on moving charges. The charge is moving with this velocity in a magnetic field of this. Find the force. And we're going to get to the right-hand rule. This is right-hand rule number 1. The direction of this, and we're going to see this in a bit. So right-hand rule number 1, and we're going to go over the right-hand rules in one big slide with all of them together. So I'll get there. Find the direction and magnitude of force on moving charges. And the little caveat here, force on negative charge is in opposite direction of positive charge. Right-hand rule number 1 is for positive charge. If it's a negative charge, it's the opposite direction. So that's just an important, remember, negatives always do the opposite of positives. Whatever a positive charge would do, a negative charge will do the exact opposite always. Always, yeah.
So can you use the left hand for?
You can. Yeah, you can totally use the left hand for negative charges. So if you want to come into a test with a negative sign scribbled on your left hand, feel free. And a positive sign scribbled on your right hand, feel free. That is one way to do it. All right. You need to be able to find the magnetic field due to one or more wires. Find the direction and magnitude of the magnetic field due to one or more wires. So there's three types of wires. I guess kind of 4. There's a straight wire, an arc of wire, a circle wire, and a solenoid. And each of them have an equation. There's an equation for the magnetic field due to a straight wire. There's an equation for a magnetic field due to an arc of wire. There's an equation for the magnetic field due to a circle wire. There's an equation for the magnetic field due to a loop or due to a solenoid. All of those are written on the test, but it is not labeled which one is which. They all just say B equals stealth. There's 4 equations that say B equals. If you're afraid of forgetting which one's which, feel free to add that to your note card. Now, regarding the direction, that is right-hand rule number 2. The direction of the magnetic field due to a wire, we use right-hand rule 2 to figure that out. And again, on one slide, I'll put all the right-hand rules all together. That's just kind of like a little cheat sheet, but I want to point that out now. Right-hand rule number 2 is find the direction of the magnetic field due to a wire. Now notice I put here if you have more than one wire. So, let's just say you had a wire going this way and another wire going this way. And you know what? All this is in a loop of wire. And you're like, oh my gosh, that looks terrible. All you need to, and let's just say that loop is going clockwise. So it actually looks like so that's currents there, that current's there, that current's there. And I say find the magnetic field here, dead center. And I give you this distance, I give you this distance, and I give you this distance. You need to recognize that this problem is just 3 problems in one, which sounds bad. But it's literally find the magnetic field due to, let's label these. Find the magnetic field due to wire 1. Find the magnetic field due to wire 2. Find the magnetic field due to wire 3. That's the loop. You have to find the direction as well. And then you just add them together. If it's into the page, we'll call it negative. If it's out of the page, we'll call it positive. So in this example, I'll quickly do right-hand rule. Magnetic field due to wire 1 is going to be into the page. So that's B1. The magnetic field due to the second wire is going to be also into the page. And the magnetic field, oh man, I made them all into the page. Well, that's unfortunate. I'm going to change this third one just to make a point. That was pure coincidence. Let's make this one go this way instead just to prove a point. The magnetic field due to wire 3 is going to point out of the page. We're going to go over how to find that real quick. So if you want the magnetic field here at the center, so the magnetic field at that spot, we'll just call it B total, is negative B1 plus negative B2 plus positive B3. Here I just decided into the page is negative. If you want, make into the page positive. I really don't care. As long as you know that into the page and out of the pages are opposite directions. That's the main key here. So, if you have multiple wires, find the magnetic field due to one of them. Find the magnetic field due to another one. Find the magnetic field due to the other one. And that sounds way worse than it is. It's literally just an equation for each one. The equations aren't that bad. You don't even have to do any vector step you don't have to break into X and Y components because they're all in and out. So they either are positive or negative and you combine them together. But that is something you need to be able to do. If you have more than one wire, can you find the magnetic field due to several of them together? And remember, y'all, the analogy for this is just like if I said, hey, there's 3 charges. Find the electric field at that spot. Find the electric field due to one of them. Find the electric field due to another one. Find the electric field due to the other one. Combine them all together. It's the same logic, the same idea. Do one at a time. Figure out what direction they're going and add or subtract as necessary. Same exact idea, even though it looks gross. Even though it looks worse, it's the same idea. Okay, so circuits, find the direction and magnitude of the force, find the direction and magnitude of the magnetic field. And then the last thing with magnetic fields, I'll chuck this on another slide. So this is magnetic fields continued. The last thing we talked about, find the EMF generated by a loop in a changing magnetic field. So this was called Lenz's law, Faraday's law. So this was EMF equals negative in change in flux over change in time. There's a bunch of problems with that. You can practice those, have such a fun time. So be able to calculate it, was one thing, just by using this equation, where flux was BA cosine theta. So this is one of them, and then there was also there was two very specific examples, and I'll draw both of those here. If you have a rod that's moving, the EMF is BLV, where L is how big that rod is. V is how fast it's going, B is the magnetic field, and this is actually the same thing as this, a rod that's going through. So that was another specific example where a loop, if you look at this example up here, my loop here is getting bigger, so I'm getting a change. There's some magnetic field. Let's just say it's out of the page, or into the page is usually easier to draw. So there's some magnetic field everywhere. Whatever. This is a specific example, so make certain you can do problems like this. You should, like when you look through the problem set, you should see a couple of these. And then you need to be able to find the direction of current. And again, this one kind of fits in the right-hand rules a little bit. Find the direction of current. In fact, I'm going to put the rules for this one. It was just a 3-step process. And we did a bunch of examples with this on the week before spring break. 3-step process. Step 1, am I gaining or losing B? Am I gaining or losing magnetic field? And in what direction? Am I gaining magnetic field out of the page? Am I losing magnetic field out of the page? Am I gaining magnetic field into the page? Am I losing magnetic field into the page? Make magnetic field to oppose change. If I'm gaining them out of it, then I'm going to make some into it. So make some magnetic field to cancel it out. If I'm losing them, then I need to make more of them. And then use right-hand rule 2.5 to make a current that makes that B. So we'll do a couple examples of this, but this is the strat for that. Am I gaining or losing B? Am I gaining magnetic field out of the page, or am I gaining magnetic field into the page? Am I losing magnetic field out of the page, losing magnetic field into the page? Cancel it out somehow. If you're losing it, make more. If you're gaining it, make it in the other direction to cancel it out. And then the next slide is going to be right-hand rules. 2.5 is a nice little shortcut to make the current that does that. So this is basically it. This is the overview of the skills that you need. Hopefully all of it looks familiar. If not, focus on the parts that don't. Look for problems that, if there's like one on here like, ooh, I don't remember how to do that, find problems like that, quicker questions, problem sets. That's the ones to kind of look over and make sure you're good to go. This covers 85% of what you may see on the test. Kind of what I talked about. There's like 15%. There's probably one or two things here and there kind of thing. But this is the gist of what you need to know. This is most of what you need to know. If you can do all the things I just talked about, you're in a really good place. So, right-hand rule. Let's go to the cheat sheet for that. So, again, this is right-hand rule visually. Again, one of those tricky things to teach. Once you get it down, you're kind of good to go, but it's getting it down that's the tricky thing. So right-hand rule 1 and right-hand rule 2, I'm going to focus on those first. Both of these start with flat hand, thumb up. And in fact, I say start with. It should always be a flat hand, thumb up. For both right-hand rule 1 and right-hand rule 2, flat hand, thumb up. I will attempt to draw this, and it's going to be awful. There's a thumb. I draw the right number of fingers. Fantastic. This is the palm. These are the fingers. This is the thumb. I am labeling these because these are the 3 directions. The palm, whatever direction that points matters. Whatever direction your thumb points matters. Whatever direction your fingers point matter. And for you all, when you're doing right hand rule 1 and right hand rule 2, your hand needs to stay locked in that position. If you curl, like technically there's variations of this where things curl, but the way I'm going to teach it to you all, keep it locked. If you make any part of that kind of curve or pivot, it can mess things up. So the way I am teaching it to you all, there's kind of other ways you can curl things, whatever. Keep it locked like that. Bam, whatever. All right, so now the way I'm going to give you this shortcut is we're going to put the variables to the fingers / palm / thumb. So for right hand rule 1, first we want to clarify, what do we use right hand rule 1 for? Force on moving charge / current. Force on moving charge / current is what you use right hand rule number 1 for. Specifically, current is positive charge. So you know what? Force on moving positive charge. Remember, negative will be the exact opposite. Moving positive charge is current. They are the same thing. They are the exact same thing. Moving positive charge is current. Just like a moving water particle, I guess you could say, is a river. Just a very, very, very tiny one. Whatever. All right, so now there's 3 variables that we line up with these. We have force. We have velocity / current. Yeah, I don't know if I have enough room. I'm just going to put V. I'm going to trust you all know what the variables mean. V / I. I'll put current because I is annoying. So we have the force on the direction of the force. We have the direction of the velocity / current. And we have the magnetic field. I'm just B. The force is the thumb. The velocity / current is the fingers. The magnetic field is the palm. You line it up as shown. Your fingers point in the direction of the velocity of the charge / if it's current instead. Your palm points in the direction of the magnetic field. Your thumb points in the direction of the force. So let's just do a very quick and easy example of that to kind of convey that idea. So if I have a positive, and something I'm also going to put over here, on the test, I am not going to use north, south, east, west, because that's funky. On the test, everything is going to be in terms of the following. Up, down, left, right, out of the page, into the page, out, in. Everything will be worded as up, down, left, right, into the page, or out of the page, and they will match this picture. So my recommendation to you all during the test, keep your paper flat on your desk, flat on whatever, and then write this on the test somewhere and line up your fingers in those directions. If I say up, your fingers should point, in the case of you all in the room, and then I'll show the people online. So here's your paper. You have it flat on your desk. Up is at the top of your paper. Down is the bottom of your paper. Left is the left side of your paper. Right is the right side of your paper. Out of your paper is pointed away from your paper. Into your paper is into your paper. So, for those online, again, oh gosh, how's this going to look? So, up is top of the paper, down is bottom. Oh gosh, is everything mirrored? Who knows? Let's see. Is it mirrored? I have no idea. Up is up, down is down, left is left, right is right. Out of the paper is out of the paper, into the paper is into the paper. So, that is you can put that on your note card, and then immediately when you get your test, transfer it to your note card, leave your paper flat. Because if you pick up your paper, now up is towards the ceiling in the room, whereas when your paper's flat, front, it's all relative to your paper. Whatever instructions I give you are relative to your paper. So if you move your paper, then the directions move with it. Okay? So this is the best recommendation I can give. Leave it flat, write this on there, line everything up to that. So let's do an example of this to make it clear. So I have a positive charge moving up. So it's moving to the top of the paper. And I have a magnetic field that is going to the right. What is the direction of the force? So, hand is flat, thumb is up. we put our fingers in the direction it's moving. So whatever direction it's moving, that is the velocity. That's what velocity is, the direction you're moving. So your fingers point up. Now, the key to right-hand rules is realizing that you can rotate your hand. Because a lot of people, what they'll end up doing is kind of swinging their wrist around. Rotate your hand, don't bend your wrist. So, fingers point up, and then I need my magnetic field to point to the left. So I rotate it so my palm points in the direction of B, and my thumb is into the paper, into the page. Again, if that was to show you all what this looked like in the test, your paper is here, my fingers would point up, my palm would point to the right, my thumb points into the page for those online. So again, you got your hand here, so my fingers point up, I rotate my hand, so my palm points in the direction of B, my thumb points into the page. So the direction of the force is into the page. If this was a negative charge, it would be out of the page. Whatever happens to a positive charge, a negative does the opposite. So let's just draw that. If I had a negative charge instead, going up, the force would be out of the page. Negatives do the opposite of positives. Always, in every situation, when it comes to charge. All right. So that's your little cheat sheet. If you have any question that says force on a moving charge and it says anything with direction, write in rule number 1. Write in rule number 2. Direction of magnetic field due to current wire. Current carrying wire. Ugh. Let's just say due to wire. Due to current. Current wire. Great. I wanted it to line up with the other one, but it's not going to. Such is life. All right. So, right-hand rule number 2, our 3 variables are direction of current. Yeah, let's keep them lined up. Location of point of interest. And direction of B. All right, so for right-hand rule number 2, your thumb points in the direction of the current. Your fingers point in the direction of the point of interest. And your palm points in the direction of the magnetic field made by that wire. So I'll go ahead and give an example to clarify what I mean, especially this location of point of interest. You're like, what the heck does that mean? So a problem, what would a problem like this look like? A current carrying wire, a wire is carrying current up. Find the magnetic field, find the direction of the magnetic field at some point to the right. We call it point P. P for point. Find the direction of the magnetic field at point P. That is the point of interest. That's where you want to find the magnetic field. So again, we just go through the motions. Flat hand, thumb up. Thumb points in the direction of current. Woohoo. And then I can swing it so that my thumb stays up. The key is to make certain if you rotate your hand, my thumb's no longer up. I failed. Your thumb needs to stay, everything needs to stay lined up. Your thumb stays up. Your point of interest is to the right. Your palm points into the page. So if this is on the test, your thumb points in the direction of the current, which is to the top of the page. Your fingers are pointed to the point you care about, which is off to the side, to the right side, and your palm points into the page. So for those online, the thumb points up in the direction of the current. I then move my fingers so that they're pointed at the spot I care about, which is off to the right, and my palm points into the screen, into the page. So this makes a magnetic field pointed into the page. So the tricky one, I guess, with this little cheat sheet is just recognizing when I say point of interest, that's where do I want to find the magnetic field? Make my fingers point to that spot. Where do I want to find the magnetic field? Make your fingers point to that spot. So let's just, do the exact same thing on the other side, because that's pretty simple. If my point of interest is instead on the other side, same thing. Thumb still points up, but now my fingers need to point to the other side, because that's the point of interest, and my palm points out of the page. Okay, so thumb points up, I swing it so that my thumb is still up and pointed towards point P, and you get a magnetic field that points into the page. The key to right-hand rules is making certain you're hitting all of these. The most common mistake when it comes to right-hand rule is for example, someone may put their thumb up for the current, and then they'll flip it around to make it point towards a spot, and their thumb is no longer pointed up. Everything needs to line up. You need to be able to check. The two things I give you, you need to make certain your hand matches those things. So in this case, your thumb needs to stay up, your fingers need to point to the right if you're finding the right spot, or your thumb points up, point to the left spot, whatever it may be. All right, so that's right-hand rule number 2. Finding the direction of a magnetic field due to straight wire. Straight wire. I'm clarifying that because right-hand rule 2.5, direction of magnetic field due to circular wire. Yeah.
Sorry, real quick.
No, it's fine. What's up?
Can you redo the
Yeah, the left side?
yeah.
Yeah, so your thumb points up, and then the point of interest is now on the left side. So you just point your fingers to the left side, and my palm points out of the page. Yeah, so that's it. So your fingers need to point to whatever spot you care about. If the spot you care about is to the left, make your fingers point to the left. If the spot you care about is to the right, make them point to the right. And your thumb needs to stay lined with the current at all times. So if you want this side, bam, and the palm gives you the direction of the B, of the magnetic field.
How is that not very visible?
Because my thumb, yeah, so I guess this one, you kind of rotate your hand this way, this one. What's important is that your thumb stays lined up with it. So what's important here is that your fingers stay lined up with the things you're supposed to stay lined up with. Do whatever you got to do with your hands, they stay lined up. Yep. It's a good question. So the question was just, again, does it break the wrist rule? Because I said, oh, don't bend your wrist. For right hand rule 2, you kind of do have to do that. So a little unfortunate there. So this one does not have a flat hand thumbs up situation. So these two, right hand rule 1 and right hand rule 2, that's where your hand's locked in, flat hand thumbs up. That's for right hand rule 1 and right hand rule 2. Right hand rule 3, oh gosh, I'm going to have to somehow draw this. Right hand rule 3 is a thumb up and your fingers, oh goodness, how am I going to draw this? I'm going to draw it the other way, that's how. Your fingers are going to curl. Oh, look at that artistic talent. There you go. It does good enough. So in this case, right hand rule 2.5, fingers curl in the direction of current. So if current's clockwise, curl your fingers clockwise. If your current's counterclockwise, curl your fingers counterclockwise. Thumb points in direction of B. So we could put a little I on our hand here and a little B there. So this one is the easiest one. This is the easiest one. So I have a current carrying loop going counterclockwise. Find the direction of the magnetic field inside the loop. You just curl your fingers and your thumb points out of the page, and that's it. So this one is for if somebody's going in a loop. You can technically use right hand rule 2 for a circle, but this is just kind of quicker and easier. So you just curl your fingers, thumb points out, done. So the magnetic field due to this is out. Boom, out of it. Easy peasy. Not much more to say there. If the current was going the other way, so if the current was instead going clockwise, curl them clockwise. I have to rotate my whole body. Rotate them clockwise, my thumb points into the page. So if it's going clockwise, rotate your fingers, it points in. All right. So there you go. That's kind of the, put it however you want. There's kind of the examples there, but this can take up you can fit this in a pretty tiny spot if you're afraid of forgetting it. If you want, you can do your own renditions of a hand. Remember, you all are allowed to print things and then like either glue/tape them to your note card. So if you're like, man, I want a hand on there, but I can't draw a nice hand, feel free to print one out online, glue it to it, and label it. That's fine. I don't care. Again, I don't care what you do with your note card as long as it's not a flip book. As long as it's not a bunch of papers kind of done to it. You can print stuff out as long as it's just kind of attached to it, stapled, glued, taped. Just something so it's not a flip book. Cool. All right. So those are the right-hand rules. Those are the ones that notoriously are kind of tricky because they're so visual. And the reality is the best way to teach this would be I'd give you some examples and then go around and help each person individually, but I have too many people for that. So, alas, I do the best I can. And this is kind of where we're at. All right, so there's that. The last thing I want to practice with you all is, and then I'll kind of just look at some problems, whatever color you all want to look at, or if you have no idea, I'll kind of throw out some problems. Practicing this whole Lenz's law. What is the direction of current? So we practice right-hand rule number 1. We practice right-hand rule number 2. We practice right-hand rule 2.5. And this is a specific case of that. If my flux is changing, if I'm gaining magnetic field or I'm losing magnetic field, find the direction of current. Let's go ahead and just do a problem with that. So, finding direction of current due to changing magnetic flux, which is very fancy. It's called Lenz's law, Faraday's law. I'm just going to draw some pictures and we'll do some examples. Yeah.
Really quickly.
Sure.
To ask, I'm not sure if you can answer this, but on the exam, for like the questions that we just kind of went over with right-hand rule, will there be like pictures like how they are in the problem set, or they're most likely going to be like written out, like, oh, you have a.
I think it's like 50. It's like 50-50.
Okay. So
50-50. Some of them may be written out. Some of them may have a picture. Like some of them may have a picture, some may not. But whatever wording I use will be up, down, left, right.
Okay.
And that's why I want to clarify that. Yeah. So if, for example, a wording for a problem would say, a wire carries current to the left. Find the magnetic field above the wire. And that would, in that case, so the problem I just said, magnetic field or wires going to the left, find the magnetic field above the wire. That's what that problem would look like. So above would be up. And if at any point you are confused in the wording location-wise, I can help you I can clarify that for you. I do not mind clarifying that kind of stuff. I do not want the wording I use to be the thing that confuses you. So if at any point you're like, is above like out of the paper? So out of the paper, I'll always say out of the paper, or I'll say into the paper. But at any point, if you're confused, I can clarify that during the test for you all. So just kind of take some peace of mind. But yeah, up, down, left, right, into the page. Just a good question. All right, so let's go ahead. I'm debating whether or not I need writing. We'll find out. So let's just do an example. I have a loop, and it's going to enter a place where the magnetic field is pointed out of the page. Which way will current be induced? So let me go ahead and copy and paste this little cheat sheet thing over here, just so you can kind of have that as a reference as I walk through this, because this is exactly what I'm going to do. And I'm going to write out those steps. So step 1. Am I gaining or losing B, and in what direction? I am gaining B out. I'm gaining when that loop moves into the magnetic field. At some later time, it'll be here. It'll be where the magnetic field is. I have gained magnetic field out of the page. Step 2, make a magnetic field to oppose that. So if I'm gaining B out, how do I oppose that? I'm going to make a magnetic field of B that's in. How do you counteract someone pushing to the right? You push to the left. How do you counteract magnetic field going out? You make magnetic field going in. So I'm going to make some magnetic field going in. How do I make that happen? And I'll even put that in red just to clarify. Make B in. How do I make that happen? Right-hand rule 2.5. How do I make a magnetic field that's going into the page? I point my thumb into the page, and my fingers curl in the direction of the current. That's it. So my thumb is into the page. I need to make that happen. Oh, clockwise current. That's it. So you point your thumb into it because you said you need to make that happen, and that's going to... So that will be a clockwise I. So it will make a current that goes clockwise. And that's it. That's how you do this rule. Go through the steps. Am I gaining or losing, in which direction? And you know what? Let's go ahead and then do kind of the natural progression of this one. Let's say my loop is now inside of it and it's moving outside of it. So now it's in it, but now it's going to leave the magnetic field. We're going to do the same thing. So it entered the magnetic field, it made a clockwise current. Now it's going to leave the magnetic field. So at some point it's going to be off to the side. And then we'll no longer. So we do our steps. We are losing B out. How do I counteract that? I'm going to make some more magnetic field that's out. Again, I'll color code that. So I'm going to make some magnetic field that's out to counteract that change. Right-hand rule 2.5. How do you make that happen? Point your thumb out of the page. Counterclockwise. Point your thumb out. Counterclockwise. I. And that's it. Okay. So again, that's kind of a rundown on those right-hand rules and how to use them. In my opinion, the trickiest part of the test. Circuits is also a little tricky. Remember, series and parallel. That's also kind of, again, one of those to focus on. But if you can do all the right-hand rules, and you can do the math that kind of accompanies those, you're going to be good to go on that and the circuit stuff. All right. So at this point, I can make problems revolving to specific ones. The problems I'm going to kind of make up at this point are, I'll kind of look at one of these, I'll kind of look at one of these. But that's kind of the idea now. I kind of covered it in words. Now I guess we can throw some numbers into the mix. Yeah.
You really could do one with the permanent magnet, like moving closer.
Yeah. So the I wish I had it in writing here. I will not have one like that on the test. Yeah, but I can quickly. So the question was, can I do one of a magnet moving towards a loop of wire? I'll be straight up honest with you. The reason I don't have one like that on the test, because it's really hard to draw a good picture of that, and like explain that well. So like it'd be. So to that end, I'll quickly kind of show you one. So if I had a loop, and again, it's so tricky to draw. So this loop is kind of flat like this. The question was, what happens, let's just say if this thing's moving towards it. If it's moving towards it, so a magnet makes a magnetic field that points away from the north. So you're going to end up gaining it. What? I'm not giving, don't worry about it. That's the quick answer for it. I will not give one like it because honestly, it'd be nice if I could, but the reality is wording a question so it's clear what I'm even asking you for that is really tricky. So I'm just not going to bother. I want to make certain my questions are
Again, I'm testing on the physics, but it is, yeah, it's something interesting to know, but you don't have to worry about it for this. All right, so let's see. Yeah, let's just, again, I'm not going to necessarily do the math for it. Let's just give you all a problem. So, find the magnetic field at point P. All right, straight wire here. You know what? Let's just do this. All right, so I've got two wires carrying current up. We'll call this one I1. We'll call this one I2. Let's call this distance. I'm actually going to put numbers for the distance. There's a purpose for this. Let's call this one 0.1 meters away. 0.1 meters away. Let's call the radius of this thing 0.2 meters. And then wire 2, the straight wire, is also 0.1 meters away. Oh, and this loop here, we'll call this current 3. Okay. So we're just going to focus on setting up the problem, because if you had the numbers, then you could just plug them in after that. The first thing I want you to do before you do any math is I want you to practice finding the direction of the magnetic field due to each of these wires. Remember, each one makes a magnetic field. What is the direction of each of those magnetic fields at that point? So that point is that point in the center of the circle. What is the direction of the magnetic field at that point for all 3 wires? So each one, do each one. What's the direction of the magnetic field due to wire 1? What's the direction of the magnetic field due to wire 2? What's the direction of the magnetic field due to wire 3? So this is right-hand rule 2 for the straight wires. So wire 1 is pointed up. So remember, this is the flat hand one, so our thumb is pointed up. The spot we care about is to the left of the wire. So we point our fingers. Okay, sorry, on your perspective, it's to the right wire. The point you care about is to the right of the wire. I was to turn myself around. So my magnetic field is into the page. Into the page. For wire 1, the magnetic field is into the page. B1. Ideally, I'd put them all on point P, but I can't fit them all there. So they're going to kind of exist around it. Sorry. All right. Wire 2, do the same thing. It's a straight wire. Thumb points up. Make your fingers point to the spot you care about. The spot I care about is now on the left side of that wire. This is a different wire. And that is out of the page. So thumb points up, fingers point to the spot, my palm points out of the page. Circular wire, right hand rule 2.5. Curl your fingers in the direction current's going. So we curl our fingers in the direction the current's going because it's a circular loop. Points into the page. So we curl our fingers in the direction. Thumb points in. So B3. Oh, and I accidentally labeled that one wrong. B2 was out of the page. That one, B3 is going to be into the page. Okay. So if I said find the magnetic field at that point, B net is going to equal B2 is positive, it's out of the page. We're just going to say out of the page is positive. Let's just call it that to make it easier. B1 is negative because it's into the page. B3 is negative because it's into the page. When we curled our fingers around, it went into the page. And let's just go ahead. Out, positive, in, negative. X's are in, dots are out. Okay. The last thing last things is, what's the equation for a straight wire? What's the equation for a loop of wire? That is on the formula sheet. It ends up being, for a straight wire, again, this is all on the formula sheet, so I'm not doing anything crazy here. Mu naught I over 2 pi r. For a loop, it's mu naught I over 2r. So at this point, you just put these here. So B2 is going to be mu naught I2 over 2 pi r2 plus negative mu naught I1 over 2 pi r1 plus negative mu naught I3 over 2 r3. And my handwriting got gross because I ran out of space to rest my hand. But the last thing that you have to do here, once you set this up, you're basically 70% of the way there. In this problem, I gave you the currents. I gave you the R. The only thing you need to figure out now that's kind of tricky is what's the R's. So spend a few seconds, see if you can figure out what those R's are. I will tell you what they are in a second. But see if you can figure it out while I clean up my handwriting. What is the value of R1? What is the value of R2? What is the value of R3? Because that's kind of the last little trickiness to this problem. I'm going to do the easy ones first. R1 is just 0.1 meters. It's how far away wire 1 is from the point. That one's really straightforward. R3, also very straightforward. It's the radius. That's R3. It's the radius of the loop. That's 0.2 meters. R2 is the only one you have to just be careful of. R2 is the distance from I2 to the spot I care about. So you just have to look at the picture and kind of think through, what is this distance? It's 0.1 plus 0.2. That's it. Nothing crazy there, but you do have to think about it. It's not just like a easy peasy given to you. R3 is the distance is R2 is 0.1 plus 0.2. And we can see that in the picture here. We have to add the rate. Yeah, so you do it from the picture. I would 100% give you the picture if this was a problem I gave you. I would not try to put this in words because that would be so convoluted. But yeah, this is a great problem because this tests three things. This tests, can you find the direction of the magnetic field due to wires? Can you calculate the magnetic field due to a wire? Can you do it for multiple wires together? So this has a bunch of skills all together. Yeah.
We follow the same thought process for the effect of one wire on a different wire.
Yeah,
At
that
point we just follow it the same.
Yeah, so that's if you have like the force on one wire due to another wire,
Yeah.
you'd find the magnetic field where the other wire is, and then you would use the equation for the force in that wire. Yeah. So that is one that you all also should kind of keep in mind. There's an example I did of two wires. Find the force of one wire on the other wire. That is a very important problem. Very, very useful problem because it tests all the ideas. It's one I did in class, so you can kind of go through the PowerPoints. If I have two wires a distance apart, and the currents are in opposite directions, find the force of the wires on each other, find the direction of the force. That is a very useful thing to do And there's a problem just like it. So I'll draw it here. I'm not going to solve it because I've kind of done it before. It's in the problem set, and so it's all kind of worked out. 2 wires carrying current, I1, I2. Find force per length and direction. Wires going the same direction do the same thing. I will tell you all, if the wires are carrying current in opposite directions, they will repel. Always. If wires are carrying current in the same direction, they will attract. Always. So, again, feel free to write that down in your note card if you want, or know how to solve that, either one, but make certain you can do this math as well. This problem again, great problem. It incorporates a few concepts together. Can you find the magnetic field due to a wire? Can you find the force in a wire due to a magnetic field? Can you find the directions? All that good stuff. All right. Let's see, how complicated of a problem. The last one I kind of want to spend time with is just combining. I'm going to do a really simple example of it for the sake of time. And then if there's any questions you have, we'll have some time for that. So the last one is just that whole combining circuit problem. Again, this is another one that's very important. Can you combine circuits? So let's make a problem. I have a battery, resistor, resistor, resistor. Find the current. And all of these are going to be 2 ohms. 2 ohms, 2 ohms, 2 ohms. You know what? Let's make it 10 volts because 10 is a nice number to work with. Find the current at the spot shown. So I'll give you all a moment to kind of think through this problem. What do you even do? Because that's always what is the first step? If you ever see a problem with a bunch of resistors, what do you do? And then if you know what to do, start doing. So no matter what I ask you in a problem like this, no matter if I say find the current here, find the voltage here, find the net resistance, who cares what I ask you? I can guarantee you, you're going to have to combine all of these into one resistor. No matter what, that is always going to be the first step. That is always going to be something you're going to have to do. So, the first question is, all right, got to combine them into one resistor. My end goal is to have a battery and one resistor, but we got a couple steps to do before we get there. So, see if y'all can figure out which ones can I combine first. We can combine these ones together, the two, they're in series. So that's going to turn it into that one. And in series, it's so nice. This is just going to be 2 plus 2 equals 4. They're in series, they add real nice. So that one's 4 ohms. All right, now they're in parallel. Now you got to combine these ones. So we're going to combine these together, and that one's not as nice. So this resistor, 1 over R is going to equal 1 over 2 plus 1 over 4. I'm going to go ahead and show you all, whenever you're adding in parallel, it ends up being 1 over all the crap. I tend to like to write it this way personally, so that way I only have to put it in my calculator one time. To get it out of the denominator, you just do 1 over the other side. What does that equal? I'm not going to even try to do it in my head. It's not worth the risk of getting it wrong. And that's my same recommendation to you all. This is one you could potentially do in your head. But why risk it when it takes probably just as much time to plug in the calculator? 1.33333. A lot of times plugging stuff in the calculator takes less time than trying to do it in your head, and it's more likely to get it correct. So 1.33 ohms. Why did we do this? What was the whole point? We know this resistance is 1.33 ohms. We know the battery is 10 volts, so we know this voltage is 10 volts. V equals IR. So I is going to equal V over R. So I is going to equal 10 divided by 1.33, which is not a very nice number, 7.52 amps. This is not our final answer. Okay? So you have to remember what the problem was asking for. It was asking for the current here. So we brought it down to one resistor. And if I was asking for the resistance anywhere that kind of matched up here, we'd be good to go. But the problem we run in is the last step, they were in parallel. In parallel, current is not constant. In parallel, current is not constant. In parallel, voltage is constant. And that's the trick here. So now you work backwards and you take from this step here what is actually constant. In parallel, voltage is constant, which means that the voltage of this resistor is 10 volts and the voltage of this resistor is 10 volts. Now, you may quickly, and then we can find current. We know voltage, we know resistance. So the current is going to equal V over R, which is going to equal 10 over 2, which is going to equal 5 ohms. Now, looking at this question, you may realize, why do we do all this if we just could have said this is 10 volts and this is 10 volts? I am giving you all kind of a recipe for how to do these problems no matter what they look like. The better you get at these, you can sometimes realize there's shortcuts. So in this original problem, we could have realized that the 10 volt battery, that this whole branch, each branch gets 10 volts, and we could have gone from there. And some of you may realize that. I throw it out there, maybe 30%. Maybe more, maybe more. The reason I went through every step here, and I went down to one resistor and worked our way back, is because that always works. That always works no matter what the problem is. And so it's a recipe you can use for any type of problem, no matter what you do. Go down to one resistor, work your way backwards. Voltage is constant in parallel, current is constant in series. And that will get you through any problem like this, no matter what. Yeah.
Just for clarity, you put ohms instead of amps.
Oh my gosh. Oh, what a chump. Me, not you. That is correct. It should be amps. Thank you, thank you. I will put... so on some of the questions on the test, some of the answers will have wrong units. That's a good thing. Because if you know your units, you can immediately rule out those as answers. So if you know your units, it actually helps you out a lot. My Physics 1 class, I got a lot of questions during the test. Did you mean to put this unit? Yep. As one of the answers. And that's the most I could tell them. But it's a good thing when there's the wrong unit there, because you immediately can rule out, if I say find the current and it's in ohms, that's not the right answer. So, that's a good thing. Alright, so yeah, I've kind of gone through the big kind of problems of know how to do them. So at this point, if you all have any specific ones that you'd like me to do, I got you. Just let me know. Yeah.
Are you going to be doing the plot, the whatever?
No, yeah, that's a good question. In the problem set, let me go ahead and show you the problem that one of your classmates is asking about. And I only know which one they're asking about because I got that question during office hours, and it is a good question. So one of the problems in the problem set, let me scroll down to it so you can see which one it is, just to make it really clear what you don't need to be able to do. What's this one? I give the magnetic field as a function of time, and I say find the EMF. So to solve this problem, well, I'm just going to straight up tell you, before I even say anything about this, you don't need to be able to do this. All right, great. So that's some peace of mind. So that means at this point you're like, oh my gosh, so much information, you can just tune me out. The way you do end up solving this problem, in fact, I'm not going to waste the time. You don't need to worry about it. If you're curious how to solve it, you can come ask me individually, but I'm not going to, because I'm straight up telling you you don't need to be able to do it, let's not waste any time on it. Yeah.
What about number 10, like the last one?
Sure, let's look at that one. So number 10. Ooh, what happened? All right, and then you may ask yourself, why did you give us a problem that you're not going to test us on? So I make the problem sets harder than the test. I would rather over-prepare you and make the test easier than the opposite. So I do want to clarify that, because that's kind of the natural, like, why you ask us to do things you're not going to test us on? It's more so as I'm developing the test, I'm like, what do I actually want you to know? What's kind of the main things? And then I kind of clarify that. There is good stuff in this problem. There is useful things. It uses the concepts, all that stuff. If you did this problem, that's great. There's things actually that are useful that translate to other things. But I do make problems on here that are harder than the test, so that when you take the test, you say, great, this is easy. That's the goal. As opposed to the opposite. Yeah, so this problem, this is stuff that you need to know. So this is that whole moving rod. So you have a rod that's moving through a magnetic field. What is the EMF generated on it? This problem boils down to, if you see a moving rod, it's BLV. So if you see a moving rod, BLV. This, it's a moving rod, BLV. This one, it's an automobile with a radio antenna that's traveling. That is a moving rod, BLV. That's kind of the quick answer there. So this moving rod, there's charges in it. They get pushed by the magnetic field. They get pushed to the opposite ends of it. That makes a voltage. But yes, that's ends up how you kind of solve this one. And the first parts here actually are also really good. Calculate the magnetic force in an electron. That's F equals QVB. So let me even go ahead and part A. I'm giving you the equations here, but make certain you know why the heck these are the right equations. So I'm kind of just giving you all the quick and short of it, but make certain you kind of look through this one. The electric field in the rod, you end up finding the voltage first. Don't necessarily worry about B too much for this test. The potential difference between the rods, that's going to be that. What is the speed of the potential difference is that? It's the same thing, but this time I give you the voltage and I say find the velocity. So just rearranging the equation. So again, I'm showing you what equations here. You should not practice this problem with already knowing what equations to use. So you should try to look at this problem without you may remember, great, that's fine. Parts A, C, and D are good ones to kind of, hey, can I do this without looking at a picture of the equations written down? If you remember it, great, just as long as you remember how to do that on the test. If you remember that there's a moving rod and has to do with voltage and blah, 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 all that kind of stuff. Remember, y'all, when it comes to studying for this test, you can look at worked out solutions, but do that as a last resort because you want to study for the test, just like the test will be. And you won't have worked out solutions during the test. Use them to help you if you get stumped, though. That's the purpose of studying. Yeah?
Source of magnetic fields number 2.
Source of magnetic fields number 2. Yeah, this one. So this is 2 wires. Find the magnetic field due to it. So this is kind of like the one I did. So 2 straight wires, find the magnetic field here. What you're going to end up finding is that the magnetic field due to, let's call this wire 1, wire 2. The magnetic field due to wire 1 points into the page. The magnetic field due to wire 2 points out of the page. When you get B net will equal B2 plus negative B1. The The equations for the magnetic field due to a straight wire are mu naught I over 2 pi r. Let's call this one R2, I2, plus negative mu naught I over 2 pi R1. Well, it ends up I is the same, R1 and R2 are the same in the first part, so it equals 0. In the case of point 2, the magnetic field due to wire 1 is still into the page. The magnetic field due to wire 2 is also into the page. So instead of so in that case, B net equals negative B2 plus negative B1. The thing that's very important here is that R1 is that entire distance, which is 4a. So it ends up being mu naught I, they all have the same I, so I'm just going to stop putting I1, R2. 2 pi times 2, yep. 2a, sure, we'll put a negative, plus negative mu naught I over 2 pi times 4a. And again, I'll let you look through and figure out why that may be if you haven't solved that one yet. Getting this is the hard part. So I'm kind of giving you all this as a way to kind of check your work and try to kind of like a checkpoint kind of thing. But make certain you can get there, because that's the hard part. Combining those together, that's the easy step. Hitting enter on your calculator is the easy step. All right, last thing I'll mention to you all, the one thing I forgot to mention. Remember, we have, so one of the things that was really a special device we had for test 1 is a capacitor. What made a capacitor so special? It stored charge, and the electric field was the same everywhere inside it, no matter where you were. With magnetic fields, we have an equivalent to that, the solenoid. The solenoid is it's like a slinky. It's a bunch of loops of wire. Why is the solenoid special? Because the magnetic field is the same everywhere inside it, just like. Y'all remember I asked a question about capacitors and I said change the distance? Well, hit, nudge, nudge, make sure you remember solenoids are special, just like capacitors are. All right, any final questions? All right. I'll stick around if you got any individual questions, come on up, but I think that's kind of the most I can give you without kind of beating a dead horse at this point. So if you got specific questions or comments, shoot me emails. Do my best to respond. Oh, I guess there's one. Okay, so make sure you bring a calculator, note card, pencil. The withdrawal deadline is this Friday. I cannot promise you all that I'll get the multiple choice grades in by that Friday. I'm going to try, but your all's exam is that Thursday night. And then obviously I teach high school the next day, and I have to teach high school. And I will try, but there's no promises I can get your all's free response grades in by whatever the withdrawal deadline is on Friday. I'll try, but that is less than 24 hours for me to do that. And if I wasn't teaching high school, I could, but I teach high school. So I will have them done by the end of the weekend. I can promise you that. I can promise you I'll have them in by Sunday. That gives me a weekend where I'm not working.
There's no DC circuits in Nixon. It doesn't work hard.